For decades, astrophysicists agreed on exactly how the universe would die, but a massive new discovery, buried in data collected from billions of light-years away, has shattered that long-held consensus. To understand how everything ends, we have to look at what holds it all together. Isaac Newton defined gravity as the ultimate binding force, a universal pull that keeps planets orbiting stars and prevents entire galaxies from flying apart into the void. That inward pull made sense until the 1920s, when a physicist and Catholic monk named Georges Lemaitre noticed the math didn't add up. The universe was actually expanding outward from a single, unimaginably dense starting point, a moment we now call the Big Bang. This setup turned the fate of reality into a straightforward math equation. Scientists assumed that eventually, the immense collective gravity of all the stars, planets, and black holes would overpower the Big Bang's outward momentum and hit the brakes on cosmic expansion. But in 1998, telescopes pointed at distant exploding stars revealed a massive anomaly. Cosmic expansion is actively accelerating, completely defying the inward pull of gravity. This chart breaks down everything in the cosmos, and it reveals a disturbing reality. The stars, planets, and galaxies we can see are a tiny fraction of existence. An invisible counter-gravitational force is pushing everything apart. We call it dark energy, and it makes up roughly 70% of the entire universe. Because dark energy appeared to push at a constant, unyielding rate, physicists aligned on a conclusion first proposed by Lord Kelvin in 1852. As galaxies zoom away from each other, their light will fade, energy will spread out, until everything drops to near absolute zero. This slow, quiet fade to black, often called the Big Freeze or the heat death of the universe, became the universally accepted fate of reality. That certainty held until researchers built the Dark Energy Spectroscopic Instrument, or DESI. Sitting atop a mountain in Arizona, this massive telescope was designed to map exactly how the universe has expanded over the last 11 billion years. In April 2024, the DESI team released a dataset that directly challenged the most foundational assumption in cosmology, that dark energy is an unchanging universal constant. This variation suggests that the cosmological constant we've used to calculate the future for decades might actually be a variable. If the strength of dark energy is shifting, then any timeline we've built for the expansion of space is essentially a blank slate. Without the stability of a constant expansion, the universe becomes vulnerable to far more abrupt transitions. Reality isn't necessarily on a fixed path toward a quiet freeze. It's now open to sudden, violent phase changes. If dark energy starts accelerating uncontrollably, we face the Big Rip. The outward push would become so severe it would rip the fabric of space. First, gravity would fail to hold galaxies together, scattering their stars. Then, planets would be shredded away from their suns. Finally, in the last moments, the sheer force of expansion would tear apart the atoms inside living beings. But if dark energy suddenly loses its power and weakens, we get the exact opposite extreme, the Big Crunch. Without that outward push to keep things separated, gravity would aggressively retake control. The cosmic expansion would halt, reverse, and drag billions of galaxies into violent collisions with one another. Stars and planets would smash together in a blinding chain reaction of destruction. Reality would end in a superheated, infinitely dense ball of collapsing matter. Compared to the slow, quiet certainty of the Big Freeze, these newly plausible realities highlight a terrifying truth. Everything we know is completely at the mercy of dark energy's unpredictable behavior. This animation models what physicists call the bounce theory. It suggests a big crunch wouldn't permanently end reality. Instead, that extreme compression would immediately rebound, triggering a new Big Bang and starting the universe all over again. Then there are the quantum anomalies. Astrophysicists have mapped out a scenario where a bizarre blob of nothingness could suddenly appear and expand at the speed of light, deleting the universe instantly in a bubble of quantum death. Or, if we zoom out far enough, our expanding cosmos might be one isolated patch on a much larger infinite structure. In this multiverse model, entire universes can collapse and be replaced while the broader system survives forever. These theories move us past the point of simple observation and into a realm where the laws of physics suggest a reality far broader than anything we can see from Earth. The ultimate tension, whether the universe freezes, tears, or crunches, rests on identifying the exact properties of dark energy. Every measurement we take brings us closer to knowing which of these physics-breaking ends is actually ours. Every new observatory we build and every dataset we collect from the edge of space proves that reality is far stranger than our best mathematical models. The universe refuses to march quietly toward a predictable death. It is a wildly complex system, actively keeping us guessing, and it will likely surprise us right up to the very end.